Hi all, today I am Ashish Kumar of BTech CSC is going to present a presentation on switching theory and logic design given to by our teacher Dr. Kamaldeep Kaur, and I have given a question 6.11 which is stated below. The question says that a binary ripple counter uses flip-flop that triggers on the positive edge of the clock. What will be the count if the normal output of the flip-flops are connected to the clock and the complemented outputs of the flip-flop are connected to the clock? So in this question we can see that it says about binary ripple counter, and it says that it is triggered using positive edge of the clock, and in the first case we have normal outputs, and in the second case we have complemented outputs. So we have to see what does this topic what does this word says, and we will see one by one about these words, these terms. So let's see first what is counter. A counter is a sequential circuit that goes through a prescribed sequence of states upon the application of input clock signal is called a counter. A counter that follows the binary number sequence is called a binary counter. For a n-bit counter, there should be n number of flip-flops connected in the series. So here it is a circuit diagram of counter in which the input clock signal is fed as an input to the counter, and the outputs of the counter are again fed as an input to the decoding logic circuit, from which we can decode the logic and use it in any circuit. So the state diagram also suggests the same. It starts its count from 1 and goes up to the value k, and again it repeats itself until the circuit stops itself. So let's see how many types of counters are there. There are two types of counter: synchronous counter and asynchronous counter. In the case of synchronous counter, each flip-flop's clock input signal uses the same source input clock signal for its triggering. In the case of asynchronous counter, each flip-flop's output serves as the clock input signal for the next flip-flop sequence. So from the circuit diagram of synchronous counter, we can see that input clock signal is given simultaneously to both the flip-flops. And in the case of asynchronous counter, the clock input signal is only given to the first flip-flop, and for the second flip-flop the output of the first flip-flop is fed as an input clock signal to the second flip-flop. So asynchronous counters are this type of circuits. In asynchronous or ripple counters, all the bits in the counts do not change at the same time as it does change synchronously in the synchronous type of the counter. So counters can be triggered in 4 different ways: positive level, negative level, positive edged, negative edged. The counter can count in 3 different ways. It can count upwards starting from the minimum value to the maximum value. It can count down, which means starting from the maximum value and ending at minimum value, or it can count up as well as down in the same circuit. Counter can be designed using 3 types of flip-flops: JK flip-flops, T flip-flops and D flip-flops. But here in this presentation we are using only JK flip-flops, which are most versatile flip-flops and used in the counter as it shows toggle mode. In further slides we will see what is toggle mode. So for a n-bit counter, the range of count is 0 to 2n minus 1, and the number of counts that the counter will count will be 2 to the power 2n, 2 to the power n. When counting up, the sequence goes in this manner: 0, 1, 2, 3, and so on, in this way. The on counting down, the counter sequence goes in this manner: 2n minus 1, 2n minus 2, and so on, again repeating itself again and again. The states diagram also says the same. Starting from the value 0, 0, it will change only one bit at one time, and in the next state it will become 0, 1, and when the next state become present state 0, 1, and then the next state for this type of binary number will be ms will change from 0 to 1. So this number we will get. So states diagram also says the same. Starting from the value 0, it will end at 1, 1, and only one bit is changing at one time. So the counter of the the complement of the count sequence count in the reverse direction. If the uncomplemented output counts up, the complemented outputs counts down, and vice versa. The natural count sequence is run through all possible combination of bits patterns, repeating up before repeating itself. It means that if a counter starts from zero, then it will starts counting without leaving any number, which means that all possible combination will be gone through. So external logic can be used to arbitrarily cause the counter to start any count and terminate at any count, which means external logic circuit diagrams can be inserted between flip flops, which can make the counter to start at any particular value or terminate at any particular value. For example, if we want to design a counter which starts its count from 2 and at value 7, so we have to insert a logic circuit between flip flops so that it can perform this type of counting. Binary ripple counter. So let's see what this type of ripple counter is. Group of flip flops connected in spatial arrangement in which states of flip flops represents the binary number equivalent to number of pulses that have occurred at the input of the counter. So it is also called a mod x counter, where x is the number of counter states and which is equal to 2n for n number of flip flops connected in sequence. The output of the first flip flops in the sequence of arrangement of the flip flops counter is called LSB, which is least significant bit, and last flip flop is called MSB, which means the output of the last flip flops will be our most significant bit for in the binary number representation, and the output of the first flip flop will be least significant bit in our binary number representation. So let's see what is positive as triggering. In the question we have given positive as triggered counter. So we have to see what is positive as triggering in counting. So if a flip flop is responding on the low to high transition state of the input clock signal, then we say that counter is following positive edge triggering method. So let's say if this is a clock input signal, then if the counter is switching its state on this edge, which means low to high edge, then it is known as positive edge triggered. Initially, if the binary output is 0, then on the transition of input clock signal from low to high, output should toggle its states, which means output should switch to 1 until the next transition of input clock pulse comes. So we have explained the diagram. So next we will see how ripple counter acts as a frequency divider. Frequency division is main purpose of the counters. The division process is used to reduce the frequency of clock input waveform. When ripple counter is triggered using input clock signal, the frequency of output of each flip-flop in the sequence is reduced to half of its previous value. Let's say if frequency of input clock signal which is fed to first flip-flop is f0, then the frequency of output Q for the first flip-flop will be f0 by 2. And in this way, if we have n number of flip-flops connected in sequence, then for the last flip-flop we will have the frequency is equal to f0 by n. So it can be said in another way, in this way, like for a mod x counter, the output of the most significant bit flip flop, which is last flip flop, divides the input clock frequency by x. It means if first flip flop frequency is f0, then the output frequency of the last flip flop will be f0 by x. Since we are designing our counter using JK flip-flop, so it is necessary to see what is JK flip-flop, how its working is. So we have our circuit diagram of JK flip-flop. JK flip-flop is an extension of SR flip-flop because SR flip-flop have some drawbacks. So to overcome these drawbacks, we have designed JK flip-flop. The only difference in JK flip-flop is from SR flip-flop is that Q and Q complement are again fed as an input to the NAND gate in the SR flip-flop. So in this way we will get JK flip-flop. So the truth table of JK flip-flop is like this. If both J and K are different, then the output Q takes the value of the J at the next clock edge. If J and K are both low, it means both are 0 0. Then the output in the output no change will occur. It means the value that is stored in the flip-flop is shown as the output. If a J and K are both high, then it means if both are 1, then the output that we will get is complement. It means the value that is stored in the flip-flop will get complemented and shown as output. Since we are working in counting, we require toggle mode, so we will work JK flip-flop only in toggle mode. Toggle mode is in JK flip-flop is when J and K are both equal to 1. We have ignored preset and clear inputs for JK flip-flops as we are working in toggle mode only. It means we have J and K is equal to 1 and there is no use of preset and clear inputs for JK flip-flops. So let's see what first part of the question says. The normal output of the flip-flops are connected to the clock. It means the normal output, which is Q node for the 2-bit counter here. The normal output Q node is fed as an input clock signal for the second flip-flop. Since we are seeing 2-bit counter, we are using only 2 number of JK flip-flops, as number of flip-flops are directly proportional to the number of bits of the counter we are designing. So the timing diagram for this type of 2-bit counter is like this. Q1 is only responding on the positive edge of the Q node because Q node is fed as an input clock signal for the second flip-flop whose output is Q1. So this type of timing diagram we will get. Here we will get 1 1 0 0. Here 0 1 1 0 0 1 1. So putting these values in the state sequence diagram, we will get this type of state sequence diagram. Q1, which is MSB in our case, and Q node, which is LSB. Here we will initially get 1 1, which is decimal equivalent to value 3. So it will start its count from 3 and goes to on counting till its minimum value, which is value 0 0, whose decimal equivalent is value 0. So this type of counter is counting from maximum value to the minimum value. That's why these type of counters are known as down counters. So in the state diagram also have 4 number of states: 0 0 0 1 1 0 and 1 1, and it is switching its states in the circular closed manner as described by this diagram. For a 2-bit counter, we have n is equal to 2 and number of states will be 2 to the power 2 is equal to 4, and the maximum count in this case will be 2 to the power 2 minus 1 is equal to 3, while the count starts its count from the maximum value 3. In the case of 2-bit counter, the number of count that the counter will count will be is equal to 4, since 2 to the power 2 is equal to 4. Let's see what will be the count in the 3-bit counter case. For a 3-bit counter, we have to use 3 number of JK flip-flops. Similarly, the output of the preceding flip-flops are fed as an input clock signal to the next flip-flop. So this type of timing diagram we will get. So each successive output is responding on the positive edge of the previous output signal. So this type of timing diagram we will get. On putting the values of these timing diagram in state sequence diagram, we will get this type of timing diagram, state sequence diagram. Initially it will start its count from 1 1 1, whose decimal equivalent is equal to 7, and its count at 0 0 0 0, which is minimum value, which is decimal equivalent to 0. And as the state diagram suggests, it will go on counting till the circuit itself stops, and it is a never ending process, so it will never stop until circuits stops itself. For a 3-bit counter, n is equal to 3 and number of states will be 2 to the power 3 is equal to 8, and maximum count in this case will be 2 to the power 3 minus 1 is equal to 7, while the count starts its maximum value from 7. For a 4-bit counter, we have to use 4 number of JK flip-flops, and similarly the circuit diagram can be visualized similarly from the previous background. This type of circuit diagram we will get. The timing diagram for 4-bit counter will be like this. Since the clock pulse which is input to the first flip flop is 16 number of states, then QD we will get this type of state timing diagram. On putting these values in the state sequence diagram, we will get this type of state sequence diagram. Here we will see that it starts its count from the value 1111, which is decimal equivalent to 15, and go on counting till its minimum value, which is value 0, whose binary equivalent is 0000. The states diagram also suggests the same. Initially it has a value 0000, and it go on counting until it reaches its maximum value 1111, and again repeating itself. The value for 4-bit counter is n is equal to 4. Number of states will be 2 to the power 4 is equal to 16, and the maximum count in this case will be 2 to the power 4 minus 1 is equal to 15, while the count starts from it's counting from the maximum value is equal to 15. So the count in the case of 4-bit counter will be is equal to 16. It means 16 times the counter will count, starting from the value 15 and going to count until value 0. So let's come to B part of our question. B part says that if the complemented output of flip-flop are connected to the clock, it means instead of normal output going to the input clock impulse for the second flip-flop, we are using complemented output of the first flip-flop as input clock signal to the second flip-flop in this case. So let's see how this works for a 2-bit counter. 2-bit counter, we have two number of JK flip-flops, and in this case, since we are using complemented output of the first flip-flop as the input clock signal for a second flip-flop, we will get this type of counter. And the timing diagram of this 2-bit counter is like this. Initially it will be 00, and then it changes state on the positive edge of the previous output, and then it will become 111.
As of now,
on
we
putting on, on putting these values in the state sequence diagram, we will get 00 as its first value, means it will start its count from the value 0, decimal equivalent 0, and counts until its maximum value, which is 1 whose decimal equivalent is 3. And as suggested by the state sequence diagram, it will have 4 states and it will count again and again these 4 values. For a 2-bit counter, we have n is equal to 2, and number of states will be 2 to the power 2 is equal to 4, and maximum count in this case will be 2 to the power 2 minus 1 is equal to 3, while the maximum count in this case will be, the count starts its counting from the value 0. It means the number of counts also in this case is 4. The only difference is that it is counting down. Here it is counting from, it is counting up, sorry, it is counting up starting from value 0 until value 3. And number of counts will be same as in the case of 2-bit down counter. It means it will count number 4, 0, 1, 2, 3. Similarly, for a 3-bit counter, we have 3 number of JK flip-flops, and the complemented output of the preceding flip-flops are again inputted as a input clock signal for the next flip-flop. This type of timing diagram we will get. This Q0, which is MSB, this type of signal we will get. It is only responding on the positive edge of the previous output, which is Q1. So on putting these values in the state sequence diagram, we will get this type of values. It will start its counting from 000, whose decimal equivalent is 0, and counts until it reaches value 7, whose binary equivalent is 1111, and it will repeat again and again these 7 states as suggested by states diagram. For a 3-bit counter, n is equal to 3, and number of states will be 2 to the power 3 is equal to 8, and maximum count in this case will be 2 to the power 3 minus 1 is equal to 7, while in this case the count starts its counting from value 0. The number of counts will be 8. For a 4-bit up counter, we have 4 number of JK flip-flops. Similarly, this circuit diagram can be visualized from the background as we have discussed before. This type of circuit diagram we will get in the 4-bit up counter. This is known as up counter because it is counting values from initially from 0 to its value 2 to the power 4, which is minus 1, which is 15. So starting from 1 0 0 0 0, which is value 0, it is counting 1 1 1 1, which is value 15, as suggested by states diagram. This number of states are repeated again and again until the circuit stops itself. For a 4-bit counter, we have n is equal to 4, and number of states will be 2 to the power 4 is equal to 16, and maximum count in this case will be 2 to the power 4 minus 1 is equal to 15, while the count starts its counting from value 0. So here is the end of our slide. So the summary of our answer to the question is that the count of the counter will be dependent on the number of states. As the number of states is 2 to the power n, the count will also be 2 to the power n. The only difference in up and down counter is that for up counter it will start its count from minimum value, which is value 0, to its maximum value depending upon the number of bits of counter we have designed. And for a down counter, it starts its count from the maximum value and at value 0, which is its minimum value. Thank you all.